Hey everybody, this is a little video presentation to help you understand some of the reaction patterns that happen when acids and bases undergo chemical changes. And you will be responsible for knowing the basic patterns and being able to predict the products. So I'm going to try and lay out like some of the different patterns, give you some examples, and then you're going to have lots of time to practice it on homeworks, WebAssign, etc. And I'll try and show you, how it can just be more general. Like I'm giving you the generalization, and then how it can be applied to like different acids, different bases, and the way the reaction would proceed. Hopefully we do have a lab on this that hopefully we will have time to do. That's always dependent. This is one that is a maybe depending on how much time we have. But I do think it's kind of fun, and it does help to solidify what you see in the lab with, the reaction that I'm presenting right here. So the first one is that anytime an acid reacts with a metal, it's going to undergo a single replacement reaction. And the products are very predictable. You're going to get a salt, which a salt, remember, is just an ionic compound. Okay. You're going to get an ionic compound, and you're going to get hydrogen gas, which remember is diatomic, so it's always going to be H2. Now, some metals react really fast with acids. Others are slower. We pretty much did this in the lab when we made the hydrogen gas. We put magnesium and hydrochloric acid, and we got magnesium chloride and hydrogen. So you can kind of see, where you've seen this before. But you can see here that if we put zinc in hydrochloric acid, then we would get zinc chloride instead of magnesium chloride. The salt that you get, okay, the ionic compound that you get is always going to be, this is very predictable, it is the cation of the metal. Like in the lab, we ended up with magnesium cations, Mg+2. In this, we're going to end up with zinc cations, which happens to be Zn+2. If I used aluminum, I'd end up with aluminum cations, Al+3. So whatever metal you use, you end up with the cation of that particular metal. And then the anion for the salt is the anion from the acid. So in the case in the lab, it was also hydrochloric acid, so it was magnesium with chloride anions. In this one, it's going to be zinc with chloride ions, because here we have zinc metal, we have hydrochloric acid, okay? So after the single replacement takes place and the zinc will replace the hydrogen, we're then going to have zinc chloride, because the zinc will join up with the Cl-1, and we have to write an appropriate formula for that. And then the other product is always hydrogen gas, which we know is always H2 because it's diatomic. If you write your formulas correctly, it should be very easy then to balance, and this one's very easy to balance by just putting a 2 in front of the HCl. The metal's not the only thing that could change. If this was, for example, instead of hydrochloric acid, and I can get rid of this line now too, instead of hydrochloric acid, let's say this was, sulfuric acid. Since there's no hydro in the front, but it ends with ic, we're dealing with the sulfate anion. And so the only difference would be that instead of zinc chloride, we would get zinc sulfate, but we would still get hydrogen gas. And how a balanced reaction would look, sulfuric acid, the sulfate anion is SO4 minus 2, so we have H2SO4, zinc sulfate plus 2 minus 2 is just one of each ion, and then the hydrogen is H2. You can see that one's already balanced. And so if you write your formulas correctly, you can, easily balance the reaction, but it's very predictable. When you put a metal with an acid, you will get an ionic compound that's made of the metal and the anion from the acid, and you will get hydrogen gas. So metals can easily be worn away by acids. You want to be very careful then about things that are acidic at home coming into contact with metals. Certain metals really resist this because they're very low reactivity. Those are the ones to the, like lower right part of the D block on the periodic table, like, silver, gold, platinum. They don't react with acids too quickly, just by the very nature of their low reactivity. And then there are acids that are pretty weak, and they take a long time to eat away and have this reaction with metals. But if you have a strong acid and a reactive metal like we had in the lab, the magnesium, you remember how quickly this reaction happened and the hydrogen gas was produced. So let's take a look at another reaction. If an acid, in this case I have acetic acid, okay, how do I know that's acetic acid? Because that's the acetate anion. So I drop the ATE and add the IC. So that's acetic acid. It is with sodium bicarbonate. So this could be a carbonate or a bicarbonate with an acid. Either one of them, you will always get a salt, water, and carbon dioxide. So the salt is going to be the positive ion from the carbonate and the negative ion from the acid. So our salt is always going to be the cation of the carbonate or bicarbonate. And then you put that with the anion of the acid. Again, it really helps to recognize your ions. I see that sodium is +1 and acetate is minus. Oh, that's messy. And acetate is -1. So that does make it pretty easy to write the formula. That doesn't mean I'm going to get it neat, but, well, better. NaC2H3O2. The name of that is sodium, which is my cation, and acetate, which was the anion in my acid. The other products are always going to be water and carbon dioxide. Oops, I ran out of room. Let me do a little better job there. I'm not too happy with how this is showing up on the green either, sorry. So water and carbon dioxide. And we could add those names as well in the word equation, because on the test, you may need to do a word equation and a formula equation. This one is already balanced. If you have a different acid, you would just get a different anion right here, but you would still get water and carbon dioxide. For example, if I mixed baking soda with hydrochloric acid, I'd get sodium chloride. If I mixed it with sulfuric acid, I'd get sodium sulfate. So whatever the anion from your acid is, you put it over here with the cation from your carbonate. Likewise, the salt could be different. For example, here, if I didn't have sodium bicarbonate, if I had potassium bicarbonate, this would be potassium acetate. If I had calcium carbonate, this would be calcium acetate. So whatever your cation is, whatever your anion is, that ends up making the salt. And the other two products, they're always water and carbon dioxide. And this is one of the ones that we see a lot in our environment. We have a lot of carbonates in our environment, like marble, limestone. There's just a lot of different rocks and granite, things that contain a lot of carbonates in them. And if they come into contact with an acid, like let's say, for example, you get a lot of acid rain on a statue that is made of marble, this is going to slowly wear away at the carbonate on the statue, usually ends up turning it into a soluble salt, water and carbon dioxide. Soluble salts will get washed away with the water. And this is why you can have, in addition to just wind and water erosion, the acid will sort of speed up that erosion process on rocks that are limestone, marble, or other carbonates in nature. So a metal oxide with water is always going to undergo a synthesis reaction and just give you one product. You're going to get a hydroxide. You're going to get a base or a hydroxide of whatever the metal is. Like here's calcium oxide, so I'm going to get calcium hydroxide. If I had sodium oxide, I'd get sodium hydroxide. If I have aluminum oxide, I get aluminum hydroxide. We see this reaction all the time in nature. Take, for example, this is how rust forms. When you have something made of iron, it'll oxidize in the air and create iron oxide, and then you get iron hydroxide. That's rust. This is what happened to the outside of the Statue of Liberty. She's made of copper. Her copper oxidized, so you have copper oxide. It rains on her. Oops. Let's just start right here and look a little nicer. So let me change my color too. So on the outside, she is copper oxide because her copper oxidized. It rained on her. And what we see as that greenish color is really copper 2 hydroxide coating the outside. This is how a lot of antacids work. When you chew them up, they're often like oxides, and they go down into your stomach and react with moisture and create a hydroxide, which helps to neutralize the acid in your stomach. So we see this reaction a lot in nature, medicines, etc. But metal oxides, when they react with water, you get a base. Now, non-metal oxides, when they react with water, you get an acid. Those of you that had me for part A, and I'll try and do this. If we don't do the lab, I'll definitely try and do this. You can talk to a solution, and the carbon dioxide from your breath reacts with it to make carbonic acid. You could also just blow through a straw into a solution, and the carbon dioxide from your breath will react with the water to make carbonic acid. So you can change the color of an acid-base indicator by making an acid, and when it neutralizes the base, you get to change the color. Like phenolphthalein would go clear because of the acid. The one that I did, the base was kind of blue, and when I made the acid, that made a yellow, and the blue and yellow, when they neutralize one another, I don't know if you guys remember, it was green. So this happens naturally too in our environment. I mean, our environment contains carbon dioxide in the air when it rains. We get a little bit of carbonic acid in the rain. Okay. Some of that's going to be in rain. And so rain naturally is going to be slightly acidic. What happens though, that where we get really bad acid rain problems is when we start to get some of these other non-metal oxides in the air, like sulfur dioxide can end up in the air from burning coal. There's a lot of sulfur in coal. They burn it. You get sulfur dioxide. It rains, and you get sulfurous. Oh my goodness. and you get sulfurous acid, which is a good bit stronger than the carbonic acid. This is sulfurous acid because that is the sulfite anion. And remember, the ite gets changed to OUS, and then because of the sulfur, we always have to stick the UR before we put the OUS. So that's sulfurous acid. So sulfur dioxide and water will make sulfurous acid. When you have something that is an engine and it pulls air in to use the oxygen to, ignite and burn the gasoline, there's nitrogen and oxygen in the air. When you pull that in your engine, you get a little nitrogen oxides that are made. They react with water to give us nitric and nitrous acids. And this is why when you have a car, you're going to have an emissions test. Instead of getting nitrogen dioxide or other nitrogen oxides into the air, the carburetor on your car removes them from the exhaust. Catalytic converter. Did I say I said the carburetor? Wrong C part. The catalytic converter on your car takes the nitrogen oxide away. And it's a catalytic converter because it converts it back into nitrogen and oxygen, uses catalyst to make it happen fast. And we want to take that out of the air, because if that's in the air and it reacts with water, we're going to get various forms of, the nitrogen acids, and that's a problem. So this is something that, that we see in nature. And then our last reaction is that of neutralization. If you have an acid and a base, they will do a double replacement to make a salt and to make water. When you have double replacement, you take the positive ion from one and you put it with the negative ion from the other. We've been practicing that a lot this year. And so I would put the sodium with the acetate. So that salt is always going to be the cation. I don't think the blue shows up that well, so let me go darker again. So the cation, there it goes again, from the base, right, with, once again, the anion from the acid. So you've got to be able to look at acid names, like this one is acetic acid. And remember, if it ends with ic and it doesn't start with hydro, the gate is thick. So we knew that was the acetate anion. So this product is sodium acetate. And the other product is just going to be water, because when you put the H with the OH, HOH, that's just water. And our base here was sodium, should be an O, hydroxide. So you have sodium hydroxide plus acetic acid gives you sodium acetate and water. So, you could try this one. Like, this is barium hydroxide. And PO4 is phosphate. So this is phosphoric acid. Got to put the OR back in there, and 8 becomes ic because the gate is thick. So when they trade, you're going to get barium phosphate and the H with the OH is just going to be water. Now, to make it easy to balance, you got to write your formulas properly. Like, barium is +2, and the phosphate is -3. So you can't just write BaPO4. You've got to write a proper formula, and then the formula for water, the HOH. And then you got to balance it. We have 3 bariums on this side on the right, so I put a 3 on the left. 2 phosphorus, so I'm going to put a 2 over here. That gives me 6 hydrogens, and 3 times 2, I have 6 hydroxides. I'm going to get 6 water molecules in this reaction. This we will definitely use a good bit. We're going to do a lab where we take an acid and a base and we use them to neutralize one another. We will have to write the chemical reaction because we need the mole ratio between our acid and our base, because we are going to do calculations in amounts and figure out some concentrations that are unknown. So this is definitely going to be a skill that you need. And any of these 5 reactions that you see here are reactions that you could encounter between, lab, worksheet, WebAssign, etc. So come back to this PowerPoint if you're not sure what it makes, and follow the patterns that have been laid out. That if you have a metal with an acid, you always get a salt and hydrogen. If you have a carbonate or a bicarbonate with an acid, you always get a salt, water, and carbon dioxide. If you have a metal oxide and water, you always get the metal hydroxide base. If you have a non-metal oxide and water, you always get an acid. And then if you have an acid and a base together, you will always get one product is a salt and the other one is water. So good luck. Homework. And so let me see here. Good luck with the homework and the WebAssigns, and hopefully we get to do this lab.